Good day, we are Group 1 and we will be presenting our CalIng 3-term project called Data Denoising. Data denoising refers to the process of removing noise from a dataset. Noise is any unwanted or irrelevant information that interferes with the signal or pattern present in the data. It can be used or caused by various factors such as measurement errors, inaccuracies, or even other sources of uncertainty in data collection. Its goal is to improvise the data quality by eliminating or minimizing the impact of noise. When noise is removed, the overall quality of the data is enhanced. Therefore, clean and accurate data is significant for various applications that includes analysis, modeling, and decision making. Common approaches include filtering, smoothing, interpolation, and advanced signal processing algorithms. For the application of the differential equation, the harmonic oscillator will be used as a second order linear differential equation to determine the vibration and frequencies and the patterns. A harmonic oscillator is therefore used, in which it is a type of physical system or mathematical model that exhibits a particular type of repetitive motion called harmonic motion or oscillation. This motion is described by resorting to a force proportional to the displacement of an equilibrium positioned and directed to the opposite to that displacement. The methods that we will be using is the HAR wavelets or the HAAR wavelets, in which it is a type of wavelet transform used in signal processing and image compression. To that, there are two types of functions in which we have scaling and wavelet function. Why are we using that method? One, because the calculations involved are very straightforward. Two, it gives the ability to separate different frequency components. And three, it provides a sparse representation of the signals.
Now that we already have an understanding of Haar wavelets, let's apply them to a sample problem. Suppose we have a data from an accelerometer that is corrupted by noise. By denoising this data using the Haar wavelet transform, we can reveal the actual vibration patterns. This issue commonly arises in mechanical and structural engineering, where accurate vibration data is crucial for monitoring machinery and infrastructure, as well as in consumer electronics for motion detection. The formulas presented are crucial for the data denoising problem using Haar wavelets. The first formula is a second order differential equation shown on the left side of the slide. This equation commonly used in mechanical and structural engineering to describe systems like vibrating machinery or structures. Here, m is the mass of the machine, c is the damping coefficient representing resistance to motion, and k is the spring constant representing the system's stiffness. The term x sub t denotes the displacement of the machine as a function of time, with d squared x over dt squared being the acceleration and dx over dt being the velocity. The second formula uses the central difference method to approximate the second derivative of the displacement function x sub t. This numerical technique is particularly useful when working with discrete data points from accelerometer. This In this context, it represents the position of the data point. T is the time interval between data points and x is the value from the data. By applying this method, we can determine the second derivatives of the denoised signal x sub t with respect to time, which helps in accurately estimating the parameters m, c, and k of the system.
Now, we can move on to the in-depth solution that can help us solve the problem. Given the dataset, we divided it by pairs to perform the R wavelet transform wherein we use the resolution formula for the average and difference I gathered as seen below.
We assume a zero point 0.5 threshold from the values from the previous slide to identify coefficients that respond to noise. We then perform the inverse Haar wavelength transform to these coefficients, as seen on the figure, to reconstruct the noise signal with threshold coefficient. We then applied second order differential equation as a simple harmonic oscillator where it represents the vibration as seen on the figure. Given the gathered data from the previous slide where we perform an inverse Haar wavelength, we assume a time interval of 1 second.
Sinusoidal function is used to determine parameters of simple harmonic oscillator given the second derivatives with respect to time, as seen in the figure. Assuming the amplitude of 2.0, angular frequency of 1.5, mass of 1.2 kilograms, and spring constant of 2.25. From the sinusoidal function, we arrive at the natural frequency of 1.12 radians and damping coefficient of 0.49. And for the last part, here are the references we obtained. Thank you for watching.